us. So today we'll be talking about something very interesting. Look at this beautiful slide. So this is our planet. We live on this planet. So everyone we know live here. So this is a picture taken with NASA Terra spacecraft. Resolution on this picture is about 1 kilometer. So basically, this is our own planet, and the thin layer of atmosphere separates us from space. So, and this is beautiful because we are looking outside the atmosphere, looking for life in the universe. How many of you think that there is life outside the atmosphere? Raise your hands. I love this. Indeed, you're right. So there is life outside the Earth's atmosphere. And this is our friends, astronauts flying on the space station. So this is the humans, this is us. And still we are looking for those little green men on Mars, and it's hard to find those. So in this presentation, I will be talking about our search for life in the universe and our way, I think, we may actually tease out a possibility of finding life in the universe using something called solar gravitational lensing. So this is the title of the talk, and basically the summary of this is the summary of recent effort that we done on the NASA funding. It was NASA Innovative Advanced Concept Studies. So we have done phase 1, phase 2, and phase 3. So NASA invested pretty much about $3 million into this work for the 4 years we have done the study. So it was continuous funding. And you see the group of colleagues who worked with us from different organizations. And now community actually is growing because now we are fundraising into making something that is flying, something we call technology demonstration mission. And step by step, we're trying to develop the technologies that will take us to the slow gravitational lens. So, but this was the beginning. Motivation for that, of course, here. Look at this. This is a nice family portrait. Our planet's in the solar system. And Konstantin Tsiolkovsky in 1911 said, look, Earth is the cradle of humanity. And so at some point, humans will leave, and we will leave the cradle, we will travel in the universe. So we are building that future. And so we are trying to find those destinations where we can go. And of course, it would be nice if those destinations will be inhabited. Not just habitable, but inhabited. And so at some point, we will find those worlds, but we're still in the search. And this is an amazing search. So this is the search in the solar system. This is a short history of solar system exploration. You see, every planet in the solar system we visited with multiple spacecraft. And of course, we looked everywhere. Many spacecraft have flown around Earth. And so, of course, wonderful Mars. We hope that we will find something on Mars. At least we're looking for for the signatures of past life. And so now we found ice, a significant amount of ice on Mars. On North Pole, there is a Korolev crater that is pretty much filled with ice. So there is ice currently on Mars, which is quite interesting. But we are looking for signs of previous life. We're looking for organic life that used to be there. So, and looking elsewhere in the solar system, I like those 4 objects. I mentioned something about Mars. So Mars is multiple missions are going to Mars. Since the year 2000, we travel there pretty much every 18 months, every 2 years. It's a traffic to Mars, and hopefully, I mean, in the near future, we'll fly there even more often. Will be exciting. But interesting targets, 2 targets around Jupiter, of course, Europa and Ganymede. And so we know that there is significant water world on Europa. And my favorite moon is the moon of Saturn. It's Enceladus. Enceladus, if you remember, when Cassini spacecraft had flown around Enceladus, it discovered the plumes emanating from the south pole of Enceladus. Essentially water, significant layer of water, the ocean on Enceladus covered with the thick sheet of ice. And essentially, as water was squeezed out from the ice, it gets into space about 100 kilometers in length. And so it's pretty much, it's ice particles already because it's frozen. But still, we are expecting to fly something there soon. And hopefully we'll be able to detect the presence of life, organic life in the ocean of Enceladus. So we're looking at different missions. Maybe at some point we'll go to Europa. We'll land on Europa. We actually put there, like with the radioisotope heating units, we'll melt the sheet of ice. We'll put the submersible, and that submersible will be going around the volcanic vents around on Europa, finding life out there. Maybe, I mean, we're talking about organic life. We're talking about extremophiles that actually live live in those very difficult, interesting environments because the energy is present there. So this is our solar system. There are no those desirable little green men anywhere, unfortunately. But so we need to look outside. We need to look into the cosmos. In our galaxy alone, there are many, many stars, and at least 50% of those stars have planets. And so we expect maybe 1 to 10 planets around those stars. So potentially we're talking about 5 trillion planets in our galaxy alone. So, and with the discoveries that we're making now, so by now we have about 5,800 planets confirmed. So there are plenty more planets, planetary discoveries that we are waiting to be sort of confirmed. So potentially we're talking about 10,000 more planets will be soon known to the community. And so there are 4,300 planetary systems. There are now some terrestrial planets, so those that we expect that have a solid surface, which is quite exciting because most of the planets we discover, they're superjupiters, and so it's very difficult to expect life being on those gaseous giants. Although we're talking about maybe Venus, and Venus is a planet which has significant temperature, but we expect life exists on the upper layers of Venusian atmosphere. So there may be some organic life in the upper layers of atmosphere. So we may fly a spacecraft to scoop the parts of the sort of to get a sample and possibly finding some organic life on Venus. So there are some interesting discussions whether or not well life may exist. So it's a very exciting. And as a physicist, for me, it's very challenging because what is life and what are we looking for? Because until we go there at some point, until humanity will travel to those discovered exoplanets and confirm the life indeed exists there, how do we confirm that life exists on those objects, but doing this remotely without traveling there? What signatures do we look for? And I guess we are looking for the talk that Sarah will be giving later today. What are the remote signatures from remote sensing that will confirm presence of life? This is exciting because we need to formulate instruments, we need to formulate observables, and actually trying to develop instruments that will be confirming life on those distant exoplanets. But so the shift in the agenda now, it's not like there is if, it's the question is when we will discover those exoplanets. And there are a fleet of different missions that are going out there, essentially those that will be discovering a lot of exoplanets pretty soon. So looking at the near, sort of in our neighborhood, and we're talking about neighborhood pretty much 100 light years away from us. So there are plenty of discoveries made by a number of missions. Kepler discovered a lot of planets here. TRAPPIST, of course, TRAPPIST-1 is an interesting target. And this chart is being updated pretty much every 3 months. So potentially it's now even more denser coverage in our neighborhood. We see many more planets. So soon we will go outside, outside. Wonderful night in Luxembourg, and we'll be standing on this platform, pointing to a sky, saying, "Look, this star has a planet. We know the planet is habitable, not yet inhabited, but basically the presence of life may exist on that planet." So it's coming soon, and we hope that and this will happen within the next 5 to 10 years. So, but moving forward, there are a number of missions that we actually developed. So those missions and telescopes we observed, of course, from ground-based telescope, Keck interferometry. So on Keck interferometry, we're looking astrometrically for potential displacements of light centroid, expecting the presence of exoplanets will be found by astrometric methods, but a number of telescopes, Spitzer, Kepler, TESS, James Webb, and Roman, and the Habitable World Observatory, those telescopes are being built, discussed, and soon the community will enjoy working with the data that will be delivered by those amazing missions. And both in Europe and, of course, in the US, there are plenty of different instruments being developed and flown, and community is actually thinking what type of signatures do we need to tease out from those observables that we get with those missions. But look, let's talk about challenges. Look, this is wonderful. This is our selfie. So it's a wonderful selfie. So this Cassini spacecraft took the image of Earth, flying around Saturn, of course. And so this is selfie that we are able to make, right? So it's wonderful. Earth is right there. And so just right there, you understand that we need to have significant light amplification to see those faint targets. So, but not only this, look at this another selfie. So Curiosity rover on January 31st, 2014 took a picture of Earth. And so it's wonderful, and you get another selfie. But look, we need to have resolution to see that Earth has actually a moon. So that's something that actually we are going back to capabilities that we can deploy in space. We need to have light amplification, we need to have resolution. And this is amazing, because ultimately what we're looking for this. This is a big star nearby, and we're looking for this tiny rock, which is nearby of that star. If you're trying to find a firefly on the background of searchlight, good luck. So it's challenging, but we are relying on dynamics, that is gravitational dynamics, that helps us to tease out those tiny displacements of optical centroid. If you do it astrometrically, if you do spectroscopically, it will be a sort of radial velocity. If you do other methods, and transit methods is another quite important. But we are dealing with the tyranny of diffraction limit. So the larger the telescope, the better the data. But in reality, what we have today, we are looking at different planets. We are able to discover the presence of exoplanets directly now with those missions, the telescopes. Look, we are able to see directly light reflected off the exoplanet 170 light years away. So basically it's a super Jupiter, and so the large distance from the parent star. And again, you see dynamics, so you see the motions of exoplanets, large super Jupiters that are orbiting very distant stars. We cannot yet go inside that exciting region, because basically this is the coronagraphic limit. We have to stop. We have to stop here, because ultimately our telescope will lose sensitivity. So we need to get inside this, because this is where we expect the terrestrial planets are going to be. And we're talking about 25 to 20 masses of Jupiter. So it's the really big gaseous planets. And so we are not actually resolving them. It's a really blob of light. It's not really resolved images of any exoplanets. One of the first images taken by Webb. So we see this again, very large distance at very large distance from Earth, 355 light years away. You see the planet 6 to 12 masses of Jupiter. We see those the presence of exoplanets directly. So now we are able to see those in very rare arrangements. We can see those directly. But if you want to make an image of our own Earth, let's take our Earth to 100 light years away. So the diameter of our planet is 13,000 kilometers. I put it at 100 light years away. To see this object with 1 pixel, we need to have access to a telescope with about 87.5 kilometers. So it's basically a simple tyranny of diffraction, lambda over d, 1.22 lambda over d times the distance. And basically, from that equation, you understand. For those of you who are familiar with Los Angeles, that's JPL, and this is Dana Point. Pretty much San Diego is nearby. So it's a 90 kilometers diameter. And suppose at some point humanity will be able to make a telescope like that. Will be built a few atoms thick, will fly something in space. That object will be removed from the solar system within about a year by the solar radiation pressure. So you need to keep that very light foil. So it pretty much it's not feasible with the technologies that we have today. It's not feasible to anticipate that things like this will be actually available in near time, to be able to make direct images with resolved images of those distant worlds. And so if you want to make image like that, remember we opened that presentation with this image. You need to multiply that figure of 90 kilometers by the number of desirable pixels. So essentially, if you want to see 100 by 100 pixels, good luck. That means 990 multiplied by 100. So that's where the tyranny of diffraction limit really comes and hits us. So in the future, building larger telescopes, of course, astronomers, when they talk to astronomers, they want to have a larger telescope. The bigger the better. But reality, there's always a limit as to how big the telescope is going to be. And so, but this is why, just let's look at what do we have today in terms of wonderful telescopes constructed on Earth. So we have starting Hale telescope on what is in Mount Palomar. So basically it's very small. This is the largest telescope that is being built now, European Extremely Large Telescope in Chile. So this is 39 meters. And this is an amazing machine that's being built, and so soon it will see the first light. So, but this is the reality, what we're able to do. So this is a 30-meter telescope, and this is used to be a shaded gray area that was extremely, overwhelmingly large telescope, was studied, so but not built, of course. So this is what we can do on the ground. Thinking about space, of course, we have a little bit more modest access to modest technologies. Kepler is 1.4 meters, Hubble is 2.4 meters, and Webb, of course, 6.5. I don't see any kilometers anywhere. So it's challenge. The reality is that either you travel there or you have to rely on something that is quite exciting. This is why we started to look on the solar gravitational lensing, because solar gravitational lensing is something that is quite unique, because this is the gift of nature that is given to us for us to actually benefit from. So we know very well that gravitational lensing exists, and when we fly spacecraft in the solar system, we account for gravitational effects routinely. So we need to account for Shapiro time delay, for gravitational displacement. So everything is known, and we are using. We now have used gravitational lensing to discover exoplanets and extragalactic exoplanets, not in the Milky Way galaxy, but outside. So potentially the presence of those objects are there. But the challenge is that those discoveries, when we make with gravitational lensing, they're not repeated. So the alignment, you have a target, you have a lens, and you have us as observers. So this alignment is not repeatable, because on the human time scales. So, but in the solar system, we have a wonderful lens called the sun. And so a lens, the sun is the best lens which we have. People ask usually, why don't we use Jupiter? Jupiter orbits. Orbits the sun first. It's very difficult to make it in a practical sense. But also the focal region for Jovian lens will be at 2200 astronomical units away. So it's very, very far away. It's not really reasonable. But with the solar gravitational lensing, what we need is to engineer alignment. And what we can do, engineering alignment is possible. So now we know what needs to be done. Flying spacecraft in very distant regions in the solar system, beyond the solar system, essentially. This is what we need. We have invested significant efforts into studying optical property of the solar gravitational lens. We know very well what it has. We know that the lens is not only monopole, there is also quadrupole, and quadrupole builds a wonderful caustic. So with the caustic, and we actually know how to account for multiple other displacements like J4, J6. So we know how to use it, and essentially with the with understanding those properties of the SGL, we essentially know how to actually fly spacecraft and how to benefit from it. In terms of optical properties, just very, very short summary. For those of you who are familiar, we'll just repeat. So the point is, when I have an exoplanet basically doesn't emit light in optical invisible. It basically emits light only in infrared. So the signal coming from exoplanet will be in two bands, essentially visible and near infrared. So when this light is reflected off the exoplanet, pretty much almost a flat wavefront travels towards the sun. It envelopes the sun from two different directions, and as you know, when the light travels by the massive body, trajectory of light is no longer a straight line. It bends towards the body. So the massive body plays the role of a lens. And so we studied the strong interference region behind the sun. We understand how interferometrically the image is formed there. So what is amazing is that the efficiency of that light amplification is proportional to the ratio of the Schwarzschild radius to the wavelength that you observe. We're talking about 11 orders of magnitude. So 11 orders of magnitude. And so, but when you average that signal over the telescope aperture, let's say if you use 1 meter aperture, we still have about 7 times 10 to the 9th. It's about 7 billion times. So this is the amazing gift from nature. In addition to that, we have a resolution which is quite exciting. Even today, we are not getting microsecond resolution for free. We are getting millisecond resolutions. We're talking about 0.5 nanoseconds. And again, here, if you remember diffraction limit, so it's lambda over d, where d is the diameter of the sun this time. And so it's very difficult to expect to build instrument that will deliver that resolution just basically for free, other than using the sun for that. So what is happening? So when that light is reflected off the exoplanet, it travels there close to the sun. When it goes around the sun, it focuses, it compresses, and so essentially that image of our Earth. So I'm using the proverbial, let's say 100 light years away, 13,000 kilometers in diameter. So that image will be compressed to a cylinder with 1.3 kilometers in diameter. 1.3 kilometers. So you need to position a 1 meter space. You need to position a telescope within this cylinder. Of course, everything is moving, and I can talk about this, how everything, because the exoplanet orbits its own star. There is a proper motion between the host star and the sun. The sun doesn't stay still because it moves within the barycentric reference frame. We know how to account for all of that, and we understand how to build a mission around this. So, but potentially what we're dealing with, if assuming everything is static, so you need to position your spacecraft within this 1.3 kilometers light field. And so if you have 1 meter telescope, essentially you are looking back at the sun. When you buy a telescope, they tell you don't point at the sun. So, but in this case, we are doing exactly the opposite. We're just looking at the sun, blocking the light from the sun with the coronagraph. And so ultimately what you will be able to see is the Einstein ring that is actually shining. Imagine yourself sitting in a movie theater, like here. We have a projector. Projector is somewhere projects light onto this. So when you sit in a movie theater, you have a screen. And so when the light field, which is sent by the projector, hits the screen, the light reflected gets into your eyes, retina forms an image, and so your brain forms an image. Now imagine if there is no screen. So the light field is still there, but you don't see anything, right? So for that, you need to go on stage. You need to look back at the projector, assuming that the image is static. And you now need to move on stage in two-dimensional fashion. And if you're able to record the brightness of the projector and understand the optical properties of the lens that projects that image, you can recover the image that is being projected. That's how gravitational lensing works in this case. You go back at the focal region of the solar gravitational lens, you look back at the sun, you block the solar light, and then you see the Einstein ring that is formed around that object. And the Einstein ring changes as you move within the light field. It changes, the brightness of it changes. But understanding the optical properties of the solar gravitational lens, you recover the image. And so the biggest challenge here is the distance where those images are formed. So we're talking about, this is our wonderful neighborhood. It's our sun, Alpha Centauri, our closest neighbor. So this is where I guess there will be the first important step for the humanity to make, actually, to reach that nearby star. And of course, conveniently in the middle of that image is the solar gravitational lens focal region. And of course, everything is logarithmic scale. You expect, there's the sun, the solar system, Voyager 1, Voyager 2 spacecraft are here. And Voyager 1 today, the distance of roughly 170 astronomical units out. It was launched in the 1970s. It took for the spacecraft traveling about 3.1 astronomical units per year. Reaching the distance took about 40 years. We need to go there faster, of course. So once we get there, we will benefit fully from what exactly is happening there. So if we get there, so just stay with me. So basically, this is, if I look back at the sun, this will be kind of this is the actual Einstein ring. But actually, if you look back at the sun, we will see something like this. Einstein ring forms around the sun. So the Einstein ring, this is the sun. The thickness of it will be 1.3 kilometers. Then I put a coronagraph on top of it. And so then the Einstein ring shines, and I will be able to record that image everywhere as I move in the solar system. So if in the image plane, if I assume that the sun is dark, there is no corona, there is no brightness, very easy. So you'll be dealing only with gravity. So this is, if I take the image here and I convolve it with the solar gravitational lens point spread function, and ultimately, if I collect the data, as I said, I will be traveling sort of in the image plane, pixel by pixel, collect the data, and use that brightness to actually now to deconvolve the image and showing. You see, if I'm able to integrate long enough, I'm getting pretty nice images here. And of course, this is I'm making the assumption that the sun is dark. There is no light. There is no corona, basically, it's only gravity. And of course, it's not true. We need to account for all of that wonderful solar brightness and solar corona. And so with the solar brightness, the brightness of the solar disk, we have designed coronagraph that actually is able to block that light from the sun. Sun now is a resolved source, so we need to be able to block the light from resolved source. And so what we need to deal with is essentially solar corona. And so if K corona, we will be if we start the focal region of solar gravitational lens begins at 548 astronomical units out. So, but at this distance, the Einstein ring still touches the surface of the sun. We need to move a little bit further away where the Einstein ring will separate from the sun, and this is where we can safely block the solar light, and then we will be dealing with the solar corona only. So if we are moving at about let's say just 600 astronomical units out. This is where the Einstein rings get separated from the sun. And if we are flying to all the way to, let's say, 900 AU, we will be safe to get the light and actually integrate the light and get a very interesting characteristics. Let's talk about something that is important, signal-to-noise ratio. Because ultimately, we need to formulate observables, and when we design mission, we need to design instruments. Reality, if I use 1 meter telescope working in the visible, and I account for all the possible noise sources, I'm talking about the sun, effects from the coronagraph, sort of the remaining light from the solar corona. With the 1 meter telescope, integrating pixel by pixel, if I integrate for 300 seconds at each pixel, my signal-to-noise ratio is pretty good. So I actually build a sonar to, let's say, 4 within, this is the different wavelength. This is visible spectrum. So in this case, if I fly 1 meter telescope, I'm able to make an image of Earth within about 7 months of integration time. And of course, you will tell me that, but Earth is rotating, right? So diurnal rotation. So how to account for that? In this case, you will see later, because we assume that essentially we are not flying single telescope, we are flying several telescopes, and with the technology that we have today, with solar sailing that we actually will be using for this mission, this is inexpensive. So potentially we're flying several of those telescopes, and we can go under the diurnal rotation. But if we're looking at the near infrared, this story is even more interesting. You look with the 40 meter telescope, because the Earth will be emitting, it is warm. So basically that near infrared light is emitted by the ex-Earth. So with the 70 centimeter telescope, our signal-noise ratio is amazing. So also very good. So, and the integration time is pretty much, it's in 1 second we get in pretty much SNR of roughly 2. So again, accounting for all of those noises that we discussed, spacecraft jitter, optical performance, and everything there. So potentially in the near infrared, where all the signatures of life are present, so we're talking about methane, oxygen, nitrogen, all of those wonderful gases that actually we think will be indicative of the present ongoing life on this exoplanet, will give us a lot of interesting information. So if we account for all of that, so now this is the parameters, this is a characteristic that we have from the solar gravitational lensing. For the most distant targets, we are now studying about 30 parsec, about 100 light years away from us. So we're still getting pretty decent resolution, 128 by 128 pixels images. So we are talking rather interesting capabilities for those faint targets that we are not going to be able to see otherwise. So that's what solar gravitational lens gives us. For nearby targets, let's say 3 parsec. So basically it's within 10 light years from us. We're talking about megapixel images of those exoplanets. Megapixel images means pretty much 25 by 25 kilometers resolution on the surface. We're talking about continental lines, topography, weather pattern. And so not only this, we can do spectroscopy with this, because spectroscopically, now we know that basically we will be able to study what type of emissions from the, it's a spatially correlated spectroscopy. Basically what it means is that we will know if there is a swamp on that exoplanet. The methane emission from that swamp will be pretty much visible. We will be able to identify where the swamp is. We'll be able to identify continental lines, oceans, the islands, and the city of Luxembourg will be imaged at least by 3 by 4 pixels. So that will be amazing. We will know where Luxembourg on that exoplanet exists. And so, but what is important is that now we will be able to tease out the very important signatures of life present on that exoplanet. Whether or not they use the same carbon fuel as we stupidly use on this planet, we will know exactly that we are not alone in this galaxy. So they do the same thing as we do. But maybe we can learn from them something that they actually will teach us something by actually, without even talking with them. They will teach us how to save our planet for much longer duration. So, but okay, I'm just going through this topic quite rapidly. But how to get there? How to get there? Because ultimately we're talking about 500, at least 500 astronomical units out, 550. So how to get there? We need, of course, a wonderful parameter to consider. It's a lifetime of a scientist. So you want to fly a mission that actually will deliver results when you're still active in science and engineering. So this is why we are building a mission that will reach the focal region of the SGL within about 20 to 25 years. So therefore, you need to fly fast. And so meaning faster than 20 astronomical units out per year. And so this is the most important parameter. If you use our chemical propulsion today, we are not going to be able to reach those velocities anytime soon. But if we use some other technologies, which I will discuss, so we need to actually move on with the solar sailing, because solar sailing seems to be at the right spot of technology and history, because now the lightweight spacecraft are being available. So spacecraft like Marco spacecraft that we built, flown to Mars, and was able to transmit data when InSight lander was landing on the North Pole of Mars. Essentially, in the real time, in real time, was transmitting the entry, descent, and landing data directly to Earth. The two Marco spacecraft 6U CubeSats. First one was built by I think it was about $9 million. The second one was built at the cost of roughly $3 million. The whole mission was $16 million. But actually, the inexpensive, very capable spacecraft. So with this, there are now many more examples in the industry that we actually can benefit from building very inexpensive spacecraft and also be very capable. Solar sails is a technology that now is ready for prime time. And we know that multiple missions were flown. We need to fly. We need to develop technology that actually will take us there. So what we have today, we did a lot of interesting assessments trying to understand what actually is possible. We looked at chemical propulsion, solar thermal propulsion, nuclear electric sail. So there are a bunch of interesting technologies. But the point is, all of them are either usually the nuclear propulsion that they used to say in 20 every year they say in 20 years from now it will be ready, and so but the reality is that its technology readiness level is pretty low. So looking at what we have today, even with the Starship that is soon to be flying quite regularly, even with the Starship we still need to have launching it. It's not enough. You still need to go to Jupiter to turn back to turn around, use gravitational maneuver and fall into the sun, and then moving by the sun you need to have something Oberth maneuver to speed you up. And so for that, thermal shielding, cost of the mission is now humongous. And we're talking about multiple spacecraft. We don't want to fly just one spacecraft. So immediately the cost of the mission is prohibitively expensive. And still it's 15 AU per year, not enough. And looking at solar thermal, pretty much all of those technologies, we looked at them and would be nice because they are, especially chemical propulsion is TRL like 12 now. So it's flying everywhere, it's wonderful. But everything else, the technology readiness level is pretty low. And the investments are not going to this area. So this is why we are looking at solar at solar sails. And the solar sails, you know, it's like on a sailboat, right? So you have a wind, you have rudder, and you have sail. On the sailcraft, you have the sail, you have solar radiation pressure, and you have reaction wheels. Pretty much analogous, and so there is a momentum transfer from the photons that are from the solar radiation pressure. The photons sort of do momentum transfer to the foil, to the sail, and essentially this is how you can move faster. So this is a type of a spacecraft I will be talking about in a few minutes. So where we have articulatable vanes. So each vane is articulatable at the wrist. Essentially, you have a fully variable thrust vector. And in this case, with a variable thrust vector, you now can move pretty much. It's like tacking against the wind when you sail. You can go almost against the solar radiation pressure, and within 7 months, you actually reach the velocities. We benefit from 3 ongoing revolutions, as I mentioned. Interplanetary small sats. We'll be talking about the masses of less than 50 kilograms. So those small sats are flown now in multiple locations. There will be more of them, especially the lunar exploration now relies on the small sats. There will be many small sats going around the moon and going now, and so there will be more spacecraft going to Mars, of course, and we are studying spacecraft going around Venus. And so looking at Enceladus as well, I'll be talking about Enceladus also. Small sats are there, and they're there to stay. They're very capable and inexpensive, which is important. Now solar sails, we have several missions flown. Icarus, Japanese mission, was flown towards Venus, and essentially that real estate on a sail was used for 3 different purposes. One is, of course, for solar radiation pressure. It was solar sailing. Then there were photovoltaic elements embedded on the sail. Essentially, they were deriving power directly from the sunlight as well. And so they were using that power to drive electric propulsion on board. So basically, combination of those technologies now allows you to think about smaller, more agile spacecraft flying elsewhere in the solar system. And so light sail. And of course, unfortunately, NeoScout didn't call home. So, but ultimately, the technology is there, and essentially, we are ready to fly a lot of expertise available there. So, and last point is that now we are building small nuclear power, where there will be planar arrays that actually will be able to actually derive power from nuclear decay and charging battery directly. So there will be some power elements available for long duration flights, essentially going beyond pretty much 5 AU. So this is how we progressed. We started with something called sun vane design, that was proposed by company Lagarde in Tustin, California. Then in our study, we were essentially designed something like this, where we have it's a truss. When you launch, everything is folded. Essentially, everything is folded, and what is happening when you deploy, you have essentially vane opens up, and another deployment opens the vane. So basically, it's very, very simple, and at least it's articulatable. So now you have a variable thrust vector at will. You potentially can articulate the thrust, and you know where to go. So this is a full autonomous sailcraft. With this, this design is scalable to a very significant area to mass ratio, which is very important parameter. Leverages truss advances. A lot of interesting design features integrated into this spacecraft. So now we actually developed something called technology demonstration mission, and the TDM is the sailcraft that will go will have area to mass ratio 50. And if you go back to this, Icarus had area to mass ratio 1.3 meters squared per kilogram. Light sail, Planetary Society have flown around Earth, also 1.3. Now we're talking about Nia Scout had area to mass ratio 7.1 meters squared per kilogram. In our design, we already have built a sailcraft which is about 21 meters squared per kilogram, and this design is scalable to pretty much reaching 50. And so with 50, we are very much in the envelope and ready to go very far in the solar system. With the technology currently available, with the sail materials that are basically available, we can reach velocities already of 5 to 6 astronomical units out, twice the Voyager speed. Just to make it, the Voyager is the most distant spacecraft, the fastest moving spacecraft in the solar system, which moves at about 3.1 astronomical units per year. It's still very light, so the total mass of the spacecraft, and we decided not to develop any new technologies. We basically used avionics from Marco. We used avionics of all the processing, so basically from those flown spacecraft. And so for that, we have pretty much 5.4 kilograms of total mass of that vehicle. So that was the progression of the design. Now we have diamond-shaped vanes. We essentially built prototype of that vehicle. You see right here, sort of 1 to 3 scale prototype. And so the vanes and the sailcraft is here, and essentially the sailcraft is designed. We looked at the trajectory. Trajectory pretty much as we launch. So essentially, the different phasing of this trajectory will allow us to test the mechanisms, test the sort of autonomy. And within the 7 months, we are in the perihelion around the sun. And basically, once we are flying by the sun, you will use solar radiation pressure to implement some, again, sort of orbit maneuver. And with this, we'll be moving very, very fast. And so that's quite exciting. Of course, the challenge there, we looked at thermal design. With thermal design, we are pretty much, so this is untreated surfaces. When we treated all the surfaces, we understand how things are actually performing. Our design will survive at this quarter of an AU distance from the sun, which is enough for the first set of flights. So this is a summary of that sort of technology demonstration mission that we are aiming to fly within about 2 years from now, around the sun. And so with this, basically, that's the mission. Sort of it's now, if you visit Seattle, go to Company Explore, you will see this spacecraft sitting up there, showcasing the current capabilities. We were able to build it in Los Angeles, transported disassembled, transported all the way to Seattle, assembled it again. Everything is fine. So basically, just demonstrating that not only you can assemble, disassemble, but you can actually move things out. But that opens up a very important paragraph in the exploration of the solar system. Think about the following. For the last 40 years, we had only 6 spacecraft that went beyond the orbit of Jupiter. Pioneers, Voyagers, Cassini, Ulysses, New Horizons. And so basically, for the 40 years, we had pretty much, very few spacecraft that actually went up there. The challenge is that if today's graduate, sort of a graduate from Luxembourg University, she graduates getting her PhD in space sciences, and essentially she would join a science team somewhere in the reputable organization and start building the spacecraft. First proposal usually to space agency fails. Second proposal pretty much much better, also fails. But on the third proposal, assuming the team actually wins the spacecraft, the point is, by the age of 50, she will see her instrument on a launch pad. That's totally wrong. We have to change that. We have to make sure that our young generation of scientists and researchers will be able to fly their vehicles much faster at a reasonable pace. And essentially with the solar sailing, the cost of those missions, I didn't mention you the following. The cost of that mission, 19 million. 1.9. We will go around the sun with this vehicle. And so for launching, we use it as a ride share. So it will be about $1 million for ride share. And then the total mission will go around the sun and pretty much we will be going to a nearby asteroid. And that's basically with this mission. So now with this approach, it opens up a very different way of actually flying things. When the first technology demonstration missions will be flown, the next mission we would like to fly will be something called solar polar imager. Why? Because we are not constrained by ecliptic plane anymore. Chemical propulsion is very much limited to ecliptic plane. With solar sailing, we can actually change inclination about 3 degrees every 21 days. So within a year, we are totally polar. And so polar is exciting because if you remember what Cassini spacecraft seen on Saturn, the hexagonal structure on North and South Pole, heliophysicists expect the Sun will have the similar hexagonal structure on the poles. It will be exciting to see that, but also monitoring space weather will be exciting. In addition to that, another mission I'm interested in flying, look at Earth as an exoplanet. Think about this. Now the most productive method is transit spectroscopy to discover atmospheres on exoplanets. What if we look at our own Earth when it transits the Sun? Using the same technology, can we confirm life on Earth? So that will be a validation of our technology. So we will be able to observe an Earth transit the Sun, and then maybe Venus, and also Mercury, right? So we'll have a comparable planetology using the same technology that we deploy to search for life on using transit spectroscopy on the nearby exoplanets. A mission like that, you need to go only 40 lunar distances away from the Earth. And with the chemical propulsion, it's very expensive. You need to station Kippen. In case of the solar system, in case of the solar sail, it's very easy. Basically, you do this at will, and you stay there. You have photovoltaic elements embedded on a sail, potentially it provides you with a lot of power, and you can communicate. So solar sailing is the way to go. And the last point I want to make, Enceladus. Going through Enceladus, I would love to, at some point, maybe within the next 7 years, actually fly a mission through the plumes of Enceladus. But with Enceladus, it's a little bit challenge, because we need to slow down before we come to the plumes. If we come too fast, we will vaporize the molecules we would like, the very molecules that we would like to discover. So we need to have a relative velocity with respect to the plumes less than 4 kilometers a second. Although we can fly fast there, we will fly about 12 kilometers, maybe even 16 kilometers a second. But going by the plumes, we need to slow down. So this is where we are developing something in-flight assembly. When we fly several sailcraft, once they reach fast velocity, they will modularize, they will deliver different components of the infrastructure. When they fly by the sun, they will drop the sails, they will basically remove any dispersion of velocity among them, start proximity operations, dock, and then now you have fully capable spacecraft that actually will have solid rocket motor that will allow you to actually slow down on your approach to Enceladus, and then captured by the Saturnian system. So with this is my apologies. I'm going a little bit over time, but this is what we are aiming. We would like to see this planet soon. We would like to see exoplanets in very nice, vivid colors. So we have the idea how to actually go to do this. So we have understanding of solar gravitational lensing. We have developed technologies that actually will take us there. We are working with several governmental agencies that will allow us to fly solar sailing spacecraft around the moon. So then we're working with another organization that will allow us to monitor the sun, essentially for space weather. So those contracts will be implemented within a couple of years from now. Also, we are raising money to actually start flying the technology demonstration mission around the sun, and hopefully within 2 to 3 years we'll fly around the sun. And usually they say, look, to get there, you need to either live longer or move faster, and I prefer to do both. So hope you all join me. Let's move fast and live longer. So thank you very much for your attention. So this is our roadmap. By the time I'm 100 years old, I want to see that exoplanet. So thank you.